Alrighty, so today I just want to have a look at some simple dilations and reflections of quadratics. So the first thing that you might notice is that the quadratic has a line of symmetry running straight up vertically, meaning if you were to reflect it in the y-axis, nothing would actually change. That's just an important thing to be aware of because they're symmetrical around that point. If it's been translated at all, moved, slided somewhere else, then that's no longer going to be the case. But in this particular case, you can see that if I reflect it in the y-axis, nothing's going to happen. However, if I reflected it in the x-axis, something would happen. This would become y is equal to negative x squared. And it would look something like this. Alrighty, and now I've got to get my drawing ability working. Beautiful quadratic, there we go. Okay, so there's my new quadratic. Let me just put in some axes labels. I always forget to do these things. Okay, so you can see there that this would be y is equal to negative x squared. Alrighty, so that means that if there's a negative outside the front, that actually tells us that it's been reflected. Since it's been reflected, that tells us that it has gone from being concave up to concave down. Okay? So something's actually changed. What hasn't changed? Well, the turning point, which is also both roots, which is also the only is the y-intercept as well. So it's the y-intercept, the root, and the turning point all in one spot at 0, 0. It's a classic point. However, something more crucial has changed. What's the range of this function? Remember the range being the stretch in which the y values are possible. So if we just look at the black function, the smallest value it could be is 0, and the highest value it could be is infinity, right? So it's everywhere from 0 to infinity and beyond. So we can say that the y is in the range of 0 up to infinity. Another way we could put it is that we could say y has to be bigger or equal than 0, less than infinity, or we can just say bigger than equal to 0. Alrighty, so let's have a look at the second function. So the second function starts at 0, but then it goes downwards towards negative infinity. So the range of this function is different. So the range of the blue function is going to be y is in the range of negative infinity smaller than 0 up to 0, or you can write that as y must be less than or equal to 0, but bigger than negative infinity. But you don't have to put the bigger than negative infinity because pretty much everything's bigger than negative infinity. That's why it's so negative. Another thing you might notice is that this axis of symmetry, which is currently x equals 0, right, this vertical line that's going straight up the middle, does not change. So that, in fact, stays the same. So that's all to do with reflections. But what if I included a dilation in this? Well, with the dilation, nothing's going to change because it's only going to stretch in particular directions, either the x or the y. Now, if I had something like this, and I needed to sketch it on the same axis as a standard, well, I can do my standard graph nice and quick. So I've got 1, 1, 2, 4, and then beautiful and smooth. And then if I had to do negative 3x squared, well, the 3 tells us that there's been a dilation vertically by a factor of 3, but also, and it's been reflected in the x-axis. So I just need to perform those two translations. The reflection's easy. It goes from being a happy face to a frowny face. But to combine with that, it's also going to get a lot steeper because it's been vertically dilated, meaning stretched this way. So this point here that was at 1, 1, or sorry, 1, negative 1, is now going to be at 1, negative 3. And so this was 1, negative 1, now it's at, well, let me do the new one in a different color. So let's do the new one in red. It's going to be 1, negative 3, because it's been dilated by a factor of 3. Similarly, this one's also going to change. It was at negative 1, negative 1, and now it's going to be at negative 1, negative 3. And so the 0, 0 point stays the same, but you can see that the rest of the points are going to sharply increase. But once again, you'll notice that the thing that changed the range of this function is the reflection. The dilation doesn't actually change the reflection at all. And for the most part, oh no, when you have a simple quadratic like this, the number out the front tells us what the the vertical dilation is, and the sign tells us whether it's been reflected in the x-axis or not. Alrighty, so that's a quick little introduction into some more simple standard transformations of quadratics. See you in the next one. Goodbye.